So in this video, we're going to look at the Bayesian Nash equilibrium and rationalizability concept. So in the previous video, I discussed how you can convert an extensive form game in incomplete information into a Bayesian normal form game. So once you have converted that game into the normal form, Bayesian normal form, you can apply the standard Nash equilibrium concept to find the equilibrium, and it's called, in this case, the Bayesian Nash equilibrium. So let's look at another game here, and a game in incomplete information, where one player has more information than the other player, and then we are going to convert this game into the Bayesian normal form, and then we are going to find the Bayesian Nash equilibrium of this game. So let's look at a game. So let's say nature selects the type of player one, and let's say there are two types of player one. So let's say player one can be of type 12. So let's say x equals to 12 with a probability of 2/3. So this is the probability that nature selects player one to be type 12, x equals to 12. You can call it anything, it doesn't matter. And here, x equals to 0, right? And the probability of that is 1/3. So nature determines whether player one is going to be of type 12 or type 0, okay? So player one is going to observe this. Player one knows whether he is type 12 or type 0. So you have two decision nodes for player one. And then player one can choose two actions at each node. So player one can choose A12, being type 12. So strategy is A, and B12. Okay, so A and B, these are the two strategies. And similarly here, A0 and B0. And then player two, is going to play, but player two does not know whether he is facing type 12 or type 0 of player one. So it's incomplete information in that sense. So you can connect these nodes with the dashed line to indicate that player two does not know as to which type he's playing against. And then player two has two strategies to play the game, C or D. C and D here, and then C and D here, and again C and D. So the game will end with payoffs of, let's say, 12 here, 9 for player two, 3 for player one, 6 for player two, 6 and 0, and 6 and 9. And here 0 and 9. And over here 3 and 6. And over here 6 and 0. And let's say 6 and 9. So this is the incomplete information game. So next, I will convert this game into the Bayesian normal form. And you have learned that in the previous video. So it's the same procedure we're going to apply here. Okay, so let's convert this game into the Bayesian normal form. So here, player 1 has 4 strategies. So player 1 strategy set is, let's write it down. So player 1 has 4 strategies. A12, A0, then A12, B0, so the strategies are for player 1, A12, A0, A12, B0, B12, A0, and B12 and B0. And for player 2, the strategy set consists of C and D. So then we can, so as you can see here, we have a 4x2 matrix because player 1 has 4 strategies to play the game and player 2 has 2 strategies to play the game. So I have drawn this matrix here, 4x2 matrix, and the strategies for player one is given in the rows, and for player 2 is in the columns, right? So next we have to fill in the payoffs. So let me show you a few, the payoffs in the few cells. So let's say you are looking at player 1 playing a strategy A12 and A0. So we want to find out the expected payoff of player 1 from A12, A0, and player 2 playing C. So in this case, so probability of player 1 playing A12, right, is 2/3. Nature determines this. And in that case, player 1 is going to get 12 if player 2 chooses C. And with probability 1/3, player 1 is going to play A0. And in that case, he is going to end up getting a 0 if player 2 chooses C. So this results in an expected payoff of 8. So player 1 will get 8 here. So then next we can find the expected payoff of player 2 with the same strategies, A12 and A0 from player 1 and C for player 2 here. So with 2/3 probability, player 2 is going to get 9 if he plays C, and with 1/3 probability, he's gonna get 9 if he plays C. So the expected payoff for player 2 is 9. So that goes here. Similarly, I can look at the expected payoff for player 1 when he plays A12, A0, and player 2 plays D. In this case, with 2/3 probability, player 1 will get a payoff of 9. And with 1/3 probability, player 1 is going to get 9. So in this case, the expected payoff is 9. This should be 3. And this should be 3. Okay. So with probability 2/3, player 1 is going to get 3 if player 2 plays D. And with probability 1/3, player 1 is going to get 3 if player 2 plays D. So the expected payoff is 3. So this should be 3 here for player 1. And similarly, we can look at expected payoff of player 2 when player 1 plays A12 and A0, and player 2 plays D. So now with 2/3, player 2 is going to get a payoff of 6. And with 1/3 probability, player 2 is going to get 6 again when he plays D. So the expected payoff is 6. So you can fill that in here. So this just gives you an idea of how to fill in the payoffs, this normal form, Bayesian normal form game. So you can fill in the rest, but I'm just going to do it, the calculation here on the side, and just fill in all of these for you as a reference. So here it's 10 and 6, 4 and 7, 4 and 3, 5 and 8, 6 and 0, and 6 and 9. So this is your Bayesian normal form game, the representation of the incomplete information game. So next, we need to apply the concept of Nash equilibrium here. And so basically, let's say player 2 chooses C, what is the best response for player 1 then? So clearly player 2 chooses C, the best response for player 1 is to play A12, B0. In that case, he gets 10. And if player 2 chooses D, then the best response for player 1 is to choose B12, B0. In that case, he gets 6, which is better than 3, 4, or 5. And similarly, if player 1 chooses A12, A0, then the best response for player 2 is to choose C, because it results in 9 for player 2. Otherwise, you'll get 6. And if player 1 chooses A12, B0, then the best response for player 2 is to choose D. And if player 1 chooses B12, A0, then the best response for player 2 is to play D. And if player 1 chooses B12, B0, then the best response for player 2 is to choose D. So clearly the best responses match here. And this is your Bayesian Nash equilibrium of the game.